Welcome back to Grad, Prob, Prog. I'm still Frank. So last time we talked about integration, expectation, computing expectations, and then a couple of simple sampling algorithms, importance sampling, rejection sampling. And then we did a little bit of foreshadowing about general purpose inference algorithms in the form of likelihood. Hey, Jason, nice of you to join us. A little bit of foreshadowing in the form of likelihood weighting for graphical model, general purpose probabilistic programming inference. Okay, and we left off at the point where we started to talk about Markov chain Monte Carlo. Okay, and today we're going to just do Markov chain Monte Carlo. In particular, we're going to look at Gibbs sampling and Metropolis Hastings and talk a little bit about Markov chains and explain why these algorithms work and so on and so forth. And again, on Thursday, we'll go through a model and a particular derivation of a particular advanced Markov chain Monte Carlo algorithm for some complicated generative model, just to kind of go through it and give you a feel for it while you're more focused on actually completing the homework. So we're going to talk about a bunch of different inference techniques again in the entire course. The two main families of them will be Markov chain Monte Carlo algorithms and variational inference algorithms. Variational inference we'll address later, but Markov chain Monte Carlo is kind of a workhorse, and you need to know it. One of the reasons why a traditional motivation for why you need to know it is that rejection sampling in particular fails in high dimensions or in continuous spaces, unless you're, again, conditioning on being within some set. And importance sampling also fail in high dimensions. Now, I should say that there are some caveats to both of these, right? This is true unless you have an amazing proposal distribution. And if you have an amazing proposal distribution, then importance sampling is the best algorithm you can possibly have because you can actually sample directly from the posterior. Payman, are you in Kelowna?
I'm literally in the office.
Oh, that office. Yeah, okay, I see where you're. Okay, go ahead. So rejection and importance sampling fail in high dimensions. MCMC works better in high dimensions, better than rejection and importance sampling when you don't have a well-adapted proposal. And there are a bunch of algorithms. The big ones are Metropolis Hastings, Gibbs sampling. We will, in the homework, do Metropolis Hastings within Gibbs as a general purpose algorithm. And we will touch on, I believe in lecture 10, Hamiltonian Monte Carlo, which is sort of an efficient sampling algorithm that makes use of gradients of the log density function. The point is, particularly if you look in the readings associated with these lectures, it's possible to mix and match. These algorithms are very compositional, so you can sort of run Metropolis Hastings algorithms inside of Gibbs samplers, or you can run Gibbs samplers on one part of a space and Hamiltonian Monte Carlo on another part of a space, and you can use Gibbs sampling for a little while and then Metropolis Hastings for a little while, and all of these sort of combinations work. So most of the things that you would naturally want to do work. Emma, is your hand up on purpose, or did you?
It is. I clapped accidentally, but the hand is up on purpose. I was just wondering, for proposal distributions in practice, is there like any sort of structure or guidance on how to pick them? Because from what I've seen before, it's pretty arbitrary. So I was wondering if at a higher level of probability and programming that I know, is there a structure to it?
Oh, this is an absolutely beautiful question, and one where serious mathematical minds might be put to task. To be clear, better in what sense? More likely to get high probability samples? Yeah, that's I think is a very reasonable way of thinking about it. Yes. So the principal activity of the group, of my group in probabilistic programming, has been to work on amortized inference, which is in fact actually learning a good proposal distribution for effectively importance sampling. And using the tools of probabilistic programming, you can use analyses of the structural properties of the graphs represented by first-order probabilistic programs to derive the computational structure of a good proposal, a proposal that matches the independence assumptions made in your original model, whatever it happens to be. So if you're interested in that, actually Christian, who is the technical TA of the course, you should reach out to him. And there's somebody from my group, can you put on the chat channel the paper from Stefan Webb on structured inversion of yes, this one. Faithful inversion of generative models for effective amortized inference. So I just dropped a link on the chat channel. If you're interested in, so there's kind of, this is a great distraction because this is like in my research area, right? There's kind of two things you can do. If you have one problem and you need a good proposal distribution so that you can do inference in that problem rapidly, there's all sorts of literature on how to adapt a proposal dynamically, and all of that is more or less heuristic, and generally speaking, not worth the time and trouble. You'd rather actually build better inference algorithms than you would spend time trying to dynamically make a better proposal distribution while you're running. On the other hand, if you have repeated inference applications, like happen in AI and planning and motion control and so on and so forth, if you have these kinds of things, then learning a proposal generator is well worth your time. And in fact, we've been nominated for awards and all sorts of stuff in my group for work on doing this. And the most prog-y part of it is this faithful inversion of generative models for effective amortized inference, which conveniently the compiler that you will use in homeworks 2, 3, 4, 5, and probably 6 actually supports doing for you. But we don't know how to do this for infinite dimensional probability distributions. So there's where there's a research problem right there. Like, how do we, if we have some Bayesian nonparametric model, how do we dynamically build a good structure for an importance network automatically? No clue. Anybody can dig out on that. Naomi could dig in it. I don't know. Nemrod, I don't know. I'm actually trying to get some names by doing this. Yeah. Okay. Great. Or the shadow of Payman could do it. Who knows? Okay. All right. So just remember though that inference. When I say inference, it's all about integration, and Monte Carlo integration in particular is all about sampling, right? So the key idea in Markov chain Monte Carlo is to construct and simulate a Markov chain whose equilibrium distribution is the distribution of interest, whatever that happens to be, the posterior distribution of interest or whatever, okay? Cool. So let me just jump right in and describe the two most important Markov chain Monte Carlo algorithms. The first one being Metropolis Hastings. How many of you have actually seen Metropolis Hastings before, or implemented it, or used it? Okay, ish, okay? So let's just at least read the algorithm and think about what it does, noting that you will be implementing this as a subroutine within Metropolis within, in a Metropolis within Gibbs algorithm, okay? So the Metropolis Hastings algorithm looks like this. We initialize some time index tau and some initial state x1. Okay, so x is going to be whatever the variable of interest it is, the thing whose distribution we want samples from. Okay. the distribution that we want to sample from here, just to be clear, will be P. That's P is distribution we want from which we want samples. I'll even do grammar somewhat correctly. Okay. So it is a non-terminating algorithm, a Markov chain that you simulate that generates a sequence, a forever growing sequence of samples. So this is something you should stick in the back of your head as well when we're doing probabilistic programming inference. Almost all of the objects that we're going to talk about will result in an infinite stream of samples. Okay, so just be aware that the output signature for this is a stream type. It's a list with no termination. Right. This also, for those of you who are computer scientists, suggests laziness in computation. That is something that you can definitely bake into your inference algorithms. Okay. So what Metropolis Hastings does is it proposes from some proposal distribution Q, and we'll talk about what that is in just a second. You actually don't really, we propose from some proposal distribution, which modifies your parameter vector or state vector or X in the space of X, okay, in some way, and then making an X star. And then you either set X star to be the value of XT, or you set it to be X star. Sorry, I guess that's line 3. You accept, quote unquote, accept X star with some probability called A, which basically looks at X star and XT and computes an interesting value. It's the minimum of 1, right? So we want to make this actually a probability of the ratio of P star, X star, to P X tau. So if X star is high, in other words, the probability of X star is higher under the model, you're likely to accept it, times kind of the inverse ratio of having proposed X tau from X star or vice versa. Okay, if X star is accepted, set X tau plus 1 to the value of X star. Otherwise, keep the old value. So X tau plus 1 just gets X tau. Then increment tau, and you just keep going. Okay, so graphically, what this looks like is something like this. So if this is the space of X, so X, X1, and X2, and this is P of X, we have some density here. This will be some bimodal density. Okay. We pick X1 here, something like that. Okay. And then from the position of X1, we make some proposal. We draw some jitter to X1 from some proposal distribution. And just for pedagogical convenience, let's say that X2 lands here. So like X star lands here. Fine, whatever. Okay. Now, let me simplify our thinking just a little bit here, and let's assume this is a standard thing to do, and it's right here. Actually, great. I'll just say this. Let's assume this. Okay, that our proposal distribution X Q of X star given X tau is just normal about the current value X tau. Okay? Quickly, what does that mean about this this ratio here?
It's 1.
Who said that? Why is it 1?
I mean, it's a normal. So in one case you have x tau as the mean, in the other case you have x star as the mean. So it has the
Right.
same variance. So
So it has exactly the same probability. So if we make this assumption, then this term goes away. It's easier to think about. Okay. It doesn't have to be that way, but it's easier to think about when this assumption is made. Okay. So if that's the case, then what's the value of x2? You have x1, we've sampled from Q, it's a symmetric Gaussian. We've got x star. This is x star. What's the value of x2? Is it x1 or x star?
It's x star if x star is accepted.
So correct, but is this accepted? You can actually see it from the plot.
I didn't understand that further.
To the P distribution.
Yeah, just look at the P distribution. So the P distribution is the black oval. So if you assume that this is a bimodal distribution, unfortunately, I see that one of the density contours went away. Fine. So with reasonable probability looking at this, right, x star is higher probability under P than x1 is. Okay. Yep. These are, I see that there's some confusion, like these are Gaussian humps, right? So I'm right. Yeah, I can't draw. Yeah. You get the idea. Okay, so let's say that x star has higher probability under P than x1. Then what's the value of x2?
X star.
X star.
X star. Okay, so this is not, great, equals x2. Okay, great.
But
or
doesn't
rather,
the algorithm say accept with probability?
But this is actually really important, and this is really cool. So it says to accept with probability min 1, and then the ratio. And if P of x star is greater than P of x tau, then this is greater than 1. So it always accepts. And this is actually the kind of beautiful thing about metropolis techniques. It's like the most robust algorithm you will ever deploy in any sort of Bayesian statistical or inferential framework, so on and so forth. It is like dead simple, and it just works. Okay, you can code it up, you can get bugs in it, and it's always going to work. It's also the most straightforward optimization algorithm you can possibly write, right? Because it is a hill climbing algorithm, and there's no differentiability assumptions and no nothing, right? So for the lazy amongst us, most of the time, if you need to optimize some function, you can just write it as a Metropolis Hastings thing, right? And let it go, and it's going to hill climb. And it might take forever, but it's going to hill climb. Right? It's exceedingly robust. There are some issues, and we can just go on, right? I'll just do one more iteration in case it's not clear. Although I'm guessing it's very clear. You're going to sample from some proposal distribution around this, and now if x star is here, now we don't know whether or not it would accept. It's going to accept with some probability related to this ratio here, right? So basically the point is that a Metropolis Hastings algorithm will hill climb exclusively, but then sometimes it will actually go down the hill and then start hill climbing again. Okay. Now there are some gotchas, right? Just like usual, right? And here's a canonical example of a gotcha. And I'm kind of running out of space on this slide, but I'll do it maybe down here where you can see, right? If you have some incredibly tightly peaked P and your proposal distribution is symmetric, or rather, I guess, let's assume that you're on the density, right? Then a lot of your proposals will be off the density. So we need good proposal distributions, right? Like that actually, are well tuned to the underlying density. in some way. And that's pretty much it. Okay. So there are lots of common choices of proposal distributions. One of them is to do this symmetric Gaussian thing. Another one is to just do independent metropolis hastings, which is kind of related to rejection sampling in a weird way. And I think it's in your homework. Did I put that in the homework or no? Is that one of the questions in the homework? Prove that the IH sampler satisfies detail balance. I can't remember if I stuck it in or not. I was thinking about it. Anyway, it's relatively straightforward. Okay, and if you read, for instance, the other Bayesian statistical analysis Bible, which is this. Another amazing resource. Yeah, used to be my office next door neighbor at Columbia. Yeah, so you will try to tune metropolis hastings so that you have a Q that gives you an acceptance rate of between 25 and 50%. There's lots of theory behind that, and we're not going to go into it. But it's a good and a reasonable thing to try to achieve. Okay, cool. All right, so that's one algorithm, which you could probably implement now, right? So long as you can evaluate a density, right? A couple of things to point out, I guess a couple more things to point out about this while we're on this very, very busy slide at this point. What happens if we're doing Bayesian inference? So I've just got P of X here and P of X tau here. What happens if we're trying to sample from a posterior? So in other words, let me just write it here. I actually want to sample from P of X given Y. Well, this is pretty cool actually, because when you write, this is just like a quick little Bayes rule thing. I'm just thinking about this off the top of my head, right? It's pretty cool that the density that you would evaluate here has a normalization constant, right? Okay, but if you then put this here and down here, you'll notice that in the ratio, the normalization constant cancels. So using this for posterior inference is pretty cool because you'd never have to actually evaluate the normalization constant. Okay, I always forget to mention this. It's just sort of obvious after you do this for a number of years. It's just like that's the deal, right? So that's one. Yeah, that's useful to think about and know. Cool. Okay, let's do the next algorithm. We'll talk about the theory a little bit. Yeah, so let's take some joint distribution. Again, this could be a joint posterior distribution, but let's just think about a joint distribution here of x1 to xn. And this is horrible notation, but it basically means that x is some vector, right? But we're going to say these are sets of variables, and the union of the sets of variables is equal to this entire vector x. There's subsets of the dimensions of x, and let's, for now, this is the explicit definition of Gibbs sampling, and this is very much what you're doing in homework number 1, right? Let's consider the case where we can sample exactly from some conditional distribution, xi, given all the values of all the other variables except for xi. Yeah, Andrew Gelman is the author of the textbook. Interesting character. He has a very, it's probably the most popular statistics blog in the world. Lots of drama. Okay. So give me an example of a situation in which you have a joint distribution where you can sample from all of the conditional distributions exactly because you can write down a closed form expression for all the conditional distributions.
Question 3 of homework 1.
Question 3 of homework 1? Yes? How about another one? Question 4 of homework 1.
Yeah.
Okay. Okay. So those two questions basically force you to think about deriving these conditional distributions. Okay. And if you go back to the lecture materials and the slides and that sort of stuff, you will see that the derivations, not for the normal models, but for the Dirichlet models, are basically there that for you to use it. What is the slash? You know, it's lovely having a mathematician in the audience who's like, what the hell is all this crazy notation? Slash means set minus. Great. So let's look at the algorithm, go through it, slowly, just so we know. How many of you have done Gibbs sampling before? Probably the same as before. Gibbs sampler? Ish, a few. Okay, some. All right. So let's again have our little time index tau and some, current state of the sampler, right? We'll just initialize those. Obviously, we're going to be sampling from P again, right? Cool. Awesome. So what you want to do is we're going to generate an infinite and growing sequence, or a non-terminating sequence of samples, where we cycle through all the conditional distributions for all the variables or subsets of variables in the model, right? That's the subset thing is actually kind of important. We cycle through all of the subsets that we identify. You can think of them as individual variables. That's the way you start thinking about this. And you sample first a complete, you sample one of the conditionals, so one dimension of your vector of X or set of random variables from its conditional condition on the values of all the others except for that one. Okay, so graphically it would mean, right, in some Bayes net, right? We have some Bayes net here. You would pick one of the variables, this one maybe, and sample it conditioned on the values of all of the other variables, right? And then subsequently, using the new sampled value, so this is the new sampled value here. This is the new sample value here. You sample the next one, from the next conditional of x2, given the value that you just sampled for x1. So here's the value you just sampled for x1, there and there, right? Along with all of the values for all the other random variables, minus the 2 that you've visited so far, because you're sampling x2 and you've got a value for x1. You get a new value for x2, and then you just repeat this, basically using the values that you sample as you go along and cycling through all the conditional probabilities, sampling sampling a new value for each variable in turn from its respective conditional probabilities. Okay, this is the algorithm that I strongly is there a relationship between tau and M? Is that still on here? Is that Emma? Great. Just talk. There's not so many of us. It makes me look even more disjointed than usual because I'm trying to read 6 things going on. There's a relationship between tau and M. M is the dimension of, M is the number of subsets that you've identified of all of your random variables. Okay, so again, to try to be somewhat more clear about that, again, if I have some big Bayes net, right, so on and so forth, I might choose to separate this off into, 1, 2, 3, 4, 5. Oops, I apparently can't even count. Oh, that sucks. I might choose to separate this off into Jesus. Oh, that's hilarious. 3 different subsets of variables, each of which you can write down the conditional distribution for, given the values of every other random variable. That gives you a subset of the random variables. Like, we'll get into super precise notation when we start talking in the Prog books notation, but it gives you a subset of the random variables that whose values you can, whose conditional distribution you can derive, and then you sample all of those conditioned on the values of everything else, and then you move to the next subset. So M is the number of subsets. You can think of the number of subsets. The natural thing to do is to think of the number of subsets as being equal to the number of random variables, and just sampling each random variable from its respective conditional distribution, which you have to derive from the joint distribution using the tools and techniques that we talked about before. So Gibbs sampling historically was, if you don't do metropolis within Gibbs, was confined to models in which all of the conditional distributions can be derived using, say, for instance, the Dirichlet multinomial rule that we talked about before. Okay.
I have a follow-up question.
Awesome. Thank you for talking. Appreciate it.
No problem. So the way you've written out these sets or like groupings of the random variables is in like sequential order.
Yes.
But that doesn't include sets that are like 1, 3 and not like x1, x3, but not x2. Do they have to be in sequential order? Is it like every possible set, or is it every possible set that just like builds on the previous set?
Okay, so these are the sets. So the relationship between these sets is that their union is X. But I should also say, in this particular case, the sets are disjoint. I should say that. Yeah.
Okay.
But your question is a good one, which is basically, do the sets actually have to like, do you have to go in a particular order through the sets or the variables in the model? The answer is no, definitely. But you should cycle through all of them before you start cycling through others. Although that's also actually not specifically true. You just have to make sure that you cycle through all of them eventually, and we'll get to that in just in a little while. That's actually more readable in the notes, where you look at compositions of Markov chain operators. That's really honestly where you think about it, because each one of these is a valid Markov chain operator. But in order for the Gibbs kernel to satisfy detailed balance, you really need to visit all of them once. But you don't have to necessarily visit all of them once. You can do metropolizations in between, and you can mix and match in kind of crazy ways. Quick form clarification: since metropolis in Gibbs is intended for where the conditional cannot be formed, but question 4, of course, has closed form both conditionals. Are we supposed to go MH for T or W or both? No, I think for if you're talking homework question 3 or 4, or maybe I'm missing. Berend is question 4. I see. But T and W are not in question 4. That's what's confusing about that. T and W are the linear regression problems. Or am I getting the numbers wrong? Berend is 4. I thought 3 was linear regression, 4 was LDA.
I believe 3 is the graphical model with ancestral sampling. And then
okay,
6 is LDA. I forget what 4 and 5 are.
Scheisse. Okay. Anyway, The models that have the conditionals that you can do this for are the linear regression sampler, which you have to just derive, which you don't actually have to run. But LDA, you can do all in Gibbs sampling. So cool. And Payman's point, though, is that you can, in each of the subsets, and this is what we'll do in the Prog homeworks that will come later, we will run Metropolis Hastings as an approximate mechanism for sampling from a conditional distribution, which you should actually be able to do right now. Right? If I say sample from this thing using Metropolis Hastings, that's just some conditional distribution that looks like a posterior distribution. You can plug that into Metropolis Hastings and run a little Metropolis Hastings kernel to sample from that conditional. So mixing the two is kind of interesting. So you can form a subset, run Metropolis Hastings in that subset, then pick the next subset in the Gibbs sampler, run Metropolis Hastings in that subset, and so on and so forth. Okay, so that's what we refer to as Metropolis within Gibbs. Okay, so graphically, I don't know if I answered your question fully, Payman, but hopefully I did. Feel free to put stuff in the chat channel or just ask, talk. So the sample trajectories, I'm just going to go with a unimodal distribution here. So this is going to be P of X, and this will be X1, X2, right? The sample trajectories look different, right? So if we put X tau, X1 here, there are two variables, two subsets that you could have, X1 and X2 of X, right? So the first thing would be to say to sample X1 condition on the value of X2. Okay, so what is that conditional distribution here? So the conditional distribution is a renormalization or a slice of a slice of this density, right? So condition on the value of X2, X1, X tau has this particular value of X2, and it means that we're going to mess around with the value of X1. We're going to sample X1 condition on the value of X2. So maybe we sample, a new value of X1 here. And then we sample X2 condition on the value of X1. Okay, so what does that look like? It looks like a renormalized slice through the density here, right? So we sample X2, and maybe it moves it here, okay? So the actual move is always a coordinate-wise move or a subset coordinate-wise move through the density. So once you make all of the moves for all of the dimensions, then the full transition from X1 to X2 is having adjusted each of the conditional distributions. Okay. I'll do another case, right? That color doesn't work for lecturing, I guess. So here's X2. What's the conditional distribution of X1 given the value of X2? And now I know I have X sup and X sub 2. This is X. What is the the conditional distribution of X sub 1 given the value of X sub 2 in sample X sup 2? Well, it's this conditional, it's the renormalized conditional distribution on this, and maybe we get a sample of the value of X1 in X sup 2 here. And then again, we sample from a conditional probability distribution centered here in the other axis, and maybe we sample something up here. So the next sample, X3, from a Gibbs sampler is here. Okay. Any questions about the algorithm mechanics for either of these algorithms? Can you provide an outline for MH within Gibbs? I'm still confused, lol. Okay. Great. So remember, these are subsets, right? So cool. What if for a particular conditional probability distribution, this one right here, for instance, you do not have a closed form expression. But I still want a sample here. That means I want to sample, well, let me just go up to the Metropolis Hastings slide. That means that I'm choosing px star, whatever it is. So here px star is going to be px1 given x tau minus x1. Fine, okay. And we're going to have our q distributions, right? And this is going to be some new proposal x star, and this is going to be x x1 tau given x tau without x1. Bad notation, but it's good enough. Min 1, and then the q's. So what I'm saying is that for the same argument that we made for Bayes rule, right? So we had some argument that we made for using Bayes rule to sample from a posterior distribution. You will recognize that the same thing happens here, which is to say that actually, right, this thing right here is just proportional to the joint. The only thing that it's missing is the normalization constant associated with the value of all the other variables. But that happens to be the same for both of these conditionals. So those cancel. So all we have to do is evaluate the terms from the joint on top and bottom for this, and we can run a Metropolis Hastings kernel to get a sample from this conditional distribution. Does that make sense?
Yep.
Yes. Is there any other? This is actually really important because it is really going to be like the main kind of the first main general purpose inference result that we look at, or technique.
How long do you have to run the Metropolis Hastings for?
Nobody
if you
knows.
are using it inside the Gibbs sampling?
Nobody. That is a really, really good question. And the let's see, I guess the last time I really, really looked into this was the last time I taught the course. And there are papers, I believe, that establish that one or a small finite number of steps is fine. But the convergence, that convergent proofs for Metropolis within Gibbs are actually pretty nasty. Okay, so.
And also, is there any advantage in running Metropolis Hastings inside Gibbs when you can just do Metropolis Hastings?
Yes, a huge advantage, actually. That's a really good question. And the reason is going to be difficult to put on here, but I guess I don't have space here. Let me try something. Oh, yeah, look at this. Cool. I didn't know I could do that. That's awesome. There's a couple of things to point out. Maybe the most important one to point out about this is that when you have some crazy graphical model, I don't know what it is, A, B, C, D, right? And we write down the, I'll probably end up getting one that's, no, this will be fine. Okay. So let's say that we need to write down the conditional distribution of, we want to sample from the conditional distribution of B given A, C, and D. And this is going to be one step of our Gibbs sampler. We also need to be able to write down the conditional distribution of C given B, A, D, and we need to be able to write down, D given da-da-da-da, although D given everything is going to be really easy to sample from, and then P of A given everything as well. Okay, so if we have all of these conditional distributions, we can write down a Gibbs sampler and just go to town, right? if we're going to do Metropolis within Gibbs, or in any of these cases, right? But in particular, if we're doing Metropolis, what happens is we're going to end up writing down the joint distribution, right? Okay. Yeah, joint, whatever, of A, B, C, D is this, right? We're going to write down the joint distribution. We're going to use the joint distribution all over the place because every conditional distribution is proportional to this, right? So in other words, this is proportional to J. Right?
I think I missed, what is this? Is that an integral of A, B, C, D? I missed what that
This?
symbol is.
It's just the letter J.
J,
It's
okay.
standing for joint distribution. It's P. I could write P just as well. It's just some joint distribution, right? So everything is proportional to that, right? Because it's just hiding the normalization constant, which means that when you're doing Gibbs sampling, and this is getting back to your question, don't worry, when you're doing Gibbs sampling or Metropolis, when you're doing Metropolis within Gibbs, a couple of things happen, right? So if we write down the joint distribution or the acceptance ratio, min 1 minus J, A, B star, C, D, and then Q, whatever, over J, A, B, tau, assuming that all of the others are fixed to their existing values, right? MH to sample from P, B given A, C, D, okay? And, who knows? This is B tau to and B star given B tau, okay? So there's a couple of reasons why this makes sense. So one is if you write down the joint distribution, right, you can actually get computational savings from doing this Metropolis within Gibbs thing, right? In particular, when you're evaluating the ratio of the J's, you can pre-compute the fact that, for instance, you don't actually have to evaluate this because B does not appear as a free variable in any of the expressions. It doesn't appear in any of the expressions. And as you get really, really, really large expressions, the number of things that you need to compute in order to compute this Metropolis-Hastings ratio gets smaller. The other thing is that you immediately do not have to consider a joint Q proposal in the space of B, C, D, and A, which if you think about the highly correlated Gaussian that we were talking about, when you get highly structured, in particular program structured distribution spaces, or like the space over which you're computing a distribution, if it happens to be program structured, right, then it's going to be wildly correlated. There can be control flow in that, right? It is effectively impossible to write a Q function down or a proposal distribution Q for the entire ABCD space. Right? But if you're only proposing in some very small, like you're only proposing in the space of B, then you can actually say, okay, well, I know that B is normal. It's normally distributed. It's a real quantity on the real line. So let's make our proposal distribution for B normal, right? Or if I know that it's positive only or something like that. So basically you can propose small changes in small subsets of the variables. And that's still very, very advantageous because you don't have to design a proposal distribution that works over the entire space. Does that make sense?
Yeah, it makes sense.
It makes sense for everyone else? Okay, cool. Awesome. So I think you're ready. You can go off and implement them. That's great. That's really the key. So Metropolis Hastings and Gibbs, they're example Markov chain Monte Carlo sampling algorithms. Right? What lies behind them is that these algorithms are based on simulating Markov chains with carefully designed special purpose transition operators. That's actually what's happening underneath these two sort of seemingly random algorithms, of which you can actually demonstrate, and you do and will in homework, that Gibbs is just a special case of a Metropolis Hastings transition operator. To understand what's going on, understanding a little bit about Markov chains and the design of such operators, such general purpose transition operators, will lead to a better understanding of both the algorithms, sampling in general, and Monte Carlo integration. And again, really, Markov chain Monte Carlo, if you're just doing Bayesian statistics rather than sort of AI type things, is the default choice for an anytime inference algorithm. It's the first thing you should try. Ironically, will be somewhat less lazy mathematically, but it's still lazy mathematically in what we follow, right? And in particular, we're going to be talking about discrete spaces rather than continuous spaces in order to avoid all sorts of measure theoretic considerations and grossness, right? So we're going to talk about discrete spaces, but you should recognize that there is a well-developed theory for all of this stuff that reposes it on top of continuous spaces and does the correct measure theoretic calculations, that sort of thing. I'm not sure when we should have our Emma Hansen Memorial P break, as we've begun to understand the Emma Hansen feed oneself, so we have blood sugar break. But this might not be a bad time. So if we want to do an early one, we can do an early one, or I can go for another 5-10 minutes. This is a decent place to, probably the best place to break. Let's do it now. See you at 4:30. All right. Okay, cool, we're back. That was an awesome break. Okay, so fine. Markov chain, sweet. It's a little review. The first order Markov chain is, God, it's amazing, is one which for some integer m, 1 to big M, and for a sequence of random variables x1 to m, the following conditional independence property holds, which is that xm plus 1 given the value of x1 to xm is defined, is restricted to be first order Markov. It's xm plus 1 is equal to the probability of x plus m plus 1 given xm. In other words, conditionally independent of all the rest. In terms of the graphical model, we have some variable, and there is some transition from, all the way back into the past, and none of these arrows exist. Yep. Fine. To sort of foreshadow what's going to happen is we're really going to be focused on this conditional probability distribution, and x's now are going to be the entire state of our system, whatever it happens to be. All of the random variables in our graphical model, everything in our posterior distribution, so on and so forth, okay? And what we're going to be talking about is like how to design transition operators in that space that leave a transition, lead to the behavior we want. Such a Markov chain, not surprisingly, also obvious in the graphical modeling sense, can be specified by the initial distribution P of x naught. I guess I should have made this x naught. So whatever P of x naught is, there's some probability for this thing, this random variable, and then a conditional probability for each of the transitions going forward. So the transitions, and I'm using notation that you will find if you go off and actually read additional literature on this, which I find a little bit annoying. In the Markov chain Monte Carlo literature, they write transition operators like this, even though they're actually just conditional probability distributions. So they kind of go the wrong way. Okay, the transition operator is from xm to xm plus 1, right? So this conditioning bar isn't really here, it's a comma, really. So there's going to be transition operators, and that's basically the conditional probability of xm plus 1 given xm. It is, not just basically, it is. Okay. So Markov chain is called homogeneous if all the transitions are the same for all m. Okay, and when we talk about Metropolis Hastings on its own or Gibbs sampling on its own, we're always going to be using the same transition operator at every step in time, right? And when we think about when we think about Markov chain Monte Carlo in general, and if we do compositions as we talk about in the lecture notes, the composition we will just write as one. We will actually look at the composition and write it as one transition operator that is the composition of multiple, and we'll consider the Markov chain being the composition of operators. But don't worry about that. Just think about this. We're going to be doing Gibbs here, or the MH, and that is going to be a transition operator. We'll get to that in just a second, but I just want you to think about that's what's going to happen. The transition operators that the algorithms that we've already looked at are stochastic. We know that the samples are going to bounce around, and we know that they're first order Markov because they don't depend on any previous value or state besides the previous value of the sample. So we already can see that we have a Markov chain of some kind specified by the Metropolis Hastings algorithm, the Gibbs algorithm, because we transition from one part of X space, a value in X space, to another value in X space. And that transition operator is the same because the algorithm doesn't change. And the transition does not use any information from any previous value of the sample or any previously sampled values. So in a Markov chain, the marginal distribution of a particular variable can be expressed in the following way, right? It's just it's just a marginalization over the previous value, right? So P of xm plus 1 is just the sum over all of the xm values pushed through the transition operator, or the conditional probability distribution of xm plus 1 given xm. Okay, this is probably the most important characteristic of a Markov chain. Some distribution, here P star, is said to be invariant or stationary with respect to a Markov chain if the transition function of that chain leaves that distribution unchanged. So for example, here P star is the invariant distribution of the Markov chain with transition operator x prime to x. And remember, this is going from x prime to x. Usually we'll go from x to x prime, but this is going from x prime to x. Right, so we start with a sample x prime, and we move to x, right? And if we sum over all possible places where we start, and again, like I said, we're going to be dealing with discrete Markov chains here, and we'll just assume that this works for continuous, and you can go off and read that on your own if you care. If we sum over all possible initial starting positions and their probabilities, and we push them through the transition operator, then the marginal distribution, P star, is the same before and after the transition operator is applied. When we're thinking about Metropolis Hastings or Markov chain Monte Carlo in general, it's relatively clear that like trivial transition distributions or whatever are not of interest. And really the idea is to try to design general purpose transition operators that can have any distribution of interest. In other words, this T is actually going to be parameterized by our distribution P, right? So that can have any distribution of interest be their stationary distribution. And I should point out that for those of you who are like mathy and linear algebra and that sort of thing, that what you're looking at here is an eigen decomposition, right? So this, if we're in a discrete space, this T is just can be expressed in matrix form. P star can be expressed in vector form. And what you have here is an eigenvalue, P star is an eigenvector of T with eigenvalue 1. Okay. And if you go a little bit further and you recognize that T star, because of the fact that it's a conditional probability distribution, all of its, in this particular case, row vectors would be conditional probability distributions. That means that T is a stochastic matrix. And if you remember anything about stochastic matrices or want to go back to linear algebra, you will remember that stochastic matrices, their eigenspectrum is such that all of the eigenvalues besides the principal eigenvector, which has eigenvalue 1, have absolute value less than 1. That's like one of the characteristics of stochastic matrices. And that's incredibly important for why Markov chain Monte Carlo algorithms actually converge in the way that we're going to talk about, right? So when you do it in discrete spaces, you can really just actually prove almost everything by looking at the eigenspectrum of a stochastic transition matrix and going from there, okay?
So does that mean that if you start with an arbitrary P vector that you keep applying and applying and applying, at some point the only thing that's left over is this principal eigenvector, right? Because that's the only one that has eigenvalue 1. Is that why you eventually converge to the, to the stationary distribution?
That is 100% the hand wavy proof that one, like.
I'm a physicist. I am hand
wavy.
wavy.
If we have more time at the end, I can do the hand wavy proof doing that. It is exactly that. You write the stationary, the stationary distribution as the invariant distribution, and then apply the transition operator, again and again and again and again. Since all the eigenvalues are less than 1, everything goes away except for the stationary distribution, right? And that's actually a fun little, 20-second programming exercise to write down a transition matrix like this and then just reapply it and reapply it and reapply it and reapply it, and you see what ends up coming out is actually, no matter what P you put in the beginning, magic, it always converges to the stationary distribution of interest. Yeah. The stationary distribution, right? So the question is, that's 100% it. This is exactly what's going on. Can you design a T, which is parameterized by the distribution you want, right? That will, when you do this multiply by T a billion times, actually result in the stationary distribution of that process being the distribution that you parameterize T by. And if you think about what the Metropolis-Hastings algorithm is, and you did that in a discrete space, all of the transition operations would have a min 1 P over P, Q over Q operator, right? So you can actually write down the matrix and then just like multiply the crap out of it, and there you go, right? So that works in discrete spaces, and like the formal proofs for continuous spaces basically restrict you into domains where everything is bounded and reasonable, and then effectively look like big matrix multiplies anyway, right? So they're eigen decompositions of function spaces, basically. Yeah. Okay, cool. That's awesome. And since Berend is helping with the course, if you didn't understand that, I can either go through a little teeny tiny proof at the end, or you can ask Berend in his office hours whenever he has them, now that he's officially on the team. Okay. So again, we're going for parameterized transition operators. And there's a characteristic of a transition operator that's pretty cool. And it's basically what we use to design inference algorithms. If a transition operator T satisfies detail balance, it means that the number that you get when you take P star of X times the transition operator applied at X and some value X prime, that number is the same as P star of X prime times T of X prime given at X. So if a transition operator satisfies this detail balance condition with respect to a particular distribution, P star, for instance, then that distribution will be invariant under T. Okay, so this is like super simple, right? So the definition of detail balance is exactly here. So we have, you know, sum over x, P star of x prime. We have this here. This is the definition of detail balance. So we just switch x and x and x prime, basically. In other words, we plug in the value of this under detail balance. We're still summing over x prime, though. If you remember that this is now x to x prime. So t here is the probability of x prime given x. This is just p of x star as before. So this comes out of the sum because it doesn't have x prime in it. This has x prime as a descendant node. So we know that we can just marginalize that. And that is 1 for all values of x, right? That's basically the definition of t that gets us this. And that's just p star of x, which means that if you have a transition operator that satisfies detail balance, then P star will be the invariant distribution. So a Markov chain designed to satisfy detail balance will have P star as its stationary distribution. Fine, cool. And we're going to go quick through this. We are going to use these, and we're going to do these in the probabilistic programming context. But you know, if you decide to jump off into this, then you go over into a statistics department and take a series inference class. But we also have to restrict our design, our choice for T, to those that for like the number of samples m going to infinity, the distribution of the mth conditional distribution given an initial value x naught, you know, whatever, an arbitrary initialization, converges to the invariant distribution regardless of the distribution of the initial point. This Markov chain property is called ergodicity. Among other things, poorly designed T's could partition the space, the set of states in the set of all possible assignments of values to x, such that some subsets are unreachable from others. Okay. And this, you have to lift your thinking just a little bit and think that we're in the space not of individual values, but of the joint configuration vector. And you can imagine that you could set up a Markov chain such that you might not actually be able to transition from one part of state space to another. You could have like absorbing states or something like that in your Markov chain, right? Then we'll talk about that in just a second. And there's a whole bunch of properties of Markov chains which we're not going to cover, like properties like irreducibility and aperiodic, and you should be aware of these. But there's a fundamental theorem for of Markov chains, basically, which stated like this. It's pretty nice, right? If a homogeneous Markov chain, so in other words, a Markov chain whose transition operator is the same at every point in time, on a finite state space with transition probability t z to z prime, has pi as an invariant distribution, and there exists some number nu, which you can specify, which is greater than 0. Basically, it just means, look, it means this. If you take some particular point z, and you look at the worst possible scenario, so we're going to be somewhere in state space. This is now somewhere in our state space. And then we look at the smallest, we find the next point, the point that you could transition to, which has the smallest probability. Okay, so we find the point in space z, and then we look for some z prime that has the smallest probability, right? So long as the probability of transitioning from z to z prime divided by divided by the probability of z prime is greater than 0, then the Markov chain is ergodic, and the expectations computed with respect to the continuing sequence of distributional estimates pi n converge in expectation. Okay. That's kind of the main point of Markov chain Monte Carlo. So let's say this again. So this is cool, right? If pi z prime is 0, that means that like we don't really care about that, then this is, you know, trivially satisfied. This is going to be infinite, right? But any place that the distribution has support, in other words, you know, whatever, basically you have to be able to transition to it from everywhere. Or to satisfy this, so long as you can transition from anywhere, then this is satisfied. So long as you can get from Z to Z prime, you're fine, right? But if you're in some Z and you just have to make sure that there's some probability, non-zero probability of going to Z prime from each Z. So the minimum over Z and minimum over Z prime.
I have a quick question.
Yeah.
So we're looking at for when it's greater than 0. That's because it can possibly take on values of 0 as well, and negative values, or are we just trying to say we don't want it to be 0?
We don't want it to be 0. So in other words, it's totally acceptable to have 0 transition probability, right? You can say, I cannot go to a Z prime from this particular Z. But the only situation in which that's okay is if pi Z prime is also 0.
Okay. And it's not possible for it to take on negative values, right?
Not when these are probability measures. Yeah.
Okay.
Yeah. And Greg, I see you had a question. Are there similar results for higher order Markov chains? Would you converge to a stationary distribution faster in that case? Let me think about that. I don't remember results like that, but I'm sure that there's discussion. I'm not sure exactly whether or not that's I fully understand the even the implication of the question. Yeah.
No, it's fine. It was just a random question. So yeah.
Yeah, I have to think about that. The other statement is that if G, this is going to be our test function, is a real valued function of the state, then the expectation of G with respect to Pn, in other words, we're going to eventually be able to sample from we're going to be drawing samples from Pn, which is our the distribution of the nth state of the Markov chain. We're going to draw samples from that, right? The expectation of G with respect to Pn, which is just a sum over Z of Pn of Z of the test function, that's just the expected value, converges to its expectation with respect to the true distribution pi, right? So as n gets big, then if you take samples from Pn of Z, then you've computed the expectation that you want, basically, it will converge. I'm not saying in which sense it converges, but it will converge. That's cool. The problem with this particular statement is that in order to get samples from Pn, right, you actually have to run parallel chains. So you're going to start with some, I guess we're using Z on this slide. You're going to start with a Z naught, 1, Z naught 2, Z naught 3, Z naught 4, so on and so forth. And you have to run these all the way out, and then each one of these is a sample from Pn, right? So in other words, you would run these parallel chains and collect the last sample at time step n, and then you would be able to compute an expectation using those values. Okay, that's hideously. Why do we divide by pi z? That's just the condition. This is one of these. Again, the resource for this, and it's this right here. I could spend an entire lecture just basically proving this or going through Neil's proof for this. I recommend that you actually look at Neil's proof. It's actually very, very straightforward to read. And like most mathematical results of this flavor, the assumption that you make is of the form that makes the proof work, right? So that is, why do you divide by pi of z prime? It's because that's the condition necessary to show that this holds, right? There's a stronger result for Markov chains, which is extremely useful. But let's first say, towards designing general purpose Markov chain transition operators, we have to, we have one way to ensure that the T is ergodic, which is to basically have a proposal distribution that visits everywhere or can visit everywhere, right? And a sufficient condition to ensure that T has the equilibrium distribution we want by verifying, for instance, detail balance. We also need to know that averaging over simulations and samples from a Markov chain with such a T and a stationary distribution average nicely. And there is a result called the strong law of numbers for Markov chains, which is to say that if you have a sequence of samples Z naught to, if you have this sequence of distributions again, Z naught, Z1, so on and so forth, that you get from simulating a nice Markov chain having, and this is nice being basically what we've been talking about with stationary distribution pi z, then something really magical happens, which is not only can you run these parallel chains that I talked about, which is basically Neal's result, where you have to run a bunch of chains to get samples from Pn, right? You can in fact run one chain and average over the long run of that single chain and get empirical averages that in the limit converge to the true distribution. Does that make sense? In other words, we've got one chain, it's sampling Z, we're moving through a discrete space, right? And we're saying that the empirical average, right, converges to the stationary distribution. Cool. We'll look back at that again. Cool. So we have two views on computing expectations. One is that we have the fundamental theorem, so we can sample from P and Z via parallel chains and forward simulation. And then we have the strong law of large numbers, which says we can sample a single Markov chain for a long time and use all samples from the sequence. So we've got lots of problems. We don't know when the chains have burned in. In other words, when the set of samples is close enough distributed according to P star rather than being heavily dominated by the initial choice as starting point. We don't know when to stop when the expectation approximation of the integral is good enough, particularly if samples are not IID, which they won't be because they're going to be correlated because of the Markov chain. And worse, this is the thing that makes everybody uncomfortable about Markov chain Monte Carlo, but we're trying to solve a hard problem here, right? We can't parameterize the stopping time. There's no way to say when you should stop sampling in order to get a quality of estimate desired. The fortunate thing is sometimes you don't care. So in reasonable time, let's remember this Metropolis Hastings algorithm. This is exactly the same slide as in the beginning. It's just exactly what it was before. Just make sure that you have this thing in your head, because we are going to look at the result that if a transition operator T satisfies detail balance, it means that this condition holds and the Markov chain is ergodic and so on and so forth. So and then we can apply the strong law of large numbers and we get expectations that converge in the sense that we've just talked about. Okay, so what's the transition operator? The transition operator of Metropolis Hastings is stay the same with some probability and change with some probability. This is the change probability, right? Okay, so if we look at so to show that the Metropolis Hastings algorithm satisfies detail balance, note that the transition operator x to x prime is just equal to the proposal distribution. So you're going to propose from x prime from x times the probability of accepting x prime given that you started from x. Cool. So p of x times t of x comma x prime right here is just using the definition of t of x x prime is p of x times q times a. But we know what a is. The acceptance probability is min 1 ratio. So when you multiply in the ratio, and again, you have to look between these two slides to make sure that I have the ratios right, but I do. This thing comes in and cancels the denominator of the other, and it just multiplies by the 1. So you have a min 1 this, so on and so forth. Okay, so all that's happening is you have the x and x prime in different positions on both sides, and the min operator does this for you. Okay, sorry, the 1 over here does this for you, and the ratio does it over here. Min means that you can exchange the order of these arguments, right? And then when you look at that, that's just this term times the it's just, yeah, you pull this out, it's here, then you have the acceptance operator, which is the min 1 with the reciprocal in the other way, and p of x prime, this is then just p of x prime times t of x prime comma x, okay? So it's difficult to do this. It's much easier to do this with a big whiteboard, which is how I would normally do this on the side, but I don't know, can I do this? Cool. Yeah. So if you look at what's happening here, we're just putting this. Oh, don't do that. We're just putting. Hopefully, this is clear. I assume it is, or clear enough. We're putting this and multiplying it into here, onto this. When you multiply it onto this, you can multiply it in here and here. The numerator and denominator cancel, and you get this min expression. You flip the order. When you flip the order, you can pull this back out again. It looks like the acceptance ratio for the other direction, and this is just exactly detail balanced then. So the Metropolis-Hastings algorithm is a parameterized Markov chain transition operator that satisfies detail balance. Markov chain transition operators that satisfy detail balance result in ergodic Markov chains, which means that basically we'll explore the entire space, but really what it means is that if you have an ergodic Markov chain and you choose Q appropriately, in other words, something that can propose to go anywhere from anywhere else, or that's the easy way to get it, then you can apply the strong law of large numbers and compute expectations by simply simulating using a single sample sequence using the algorithm that we provided before. So there's the link, and I think that almost amazingly is on time. So that's good. But that's the point, right? So I'll just say it again, right? We looked at an algorithm. We didn't design it. Actually, like a really crazy piece of trivia. Well, we can do that in just a second. So we have the algorithm. There's a transition operator. Transition operator can be shown to satisfy detail balance. Detail balance, ergodic Markov chain. Choose Q such that this condition holds, which basically means you can transition anywhere. You get strong law of large numbers. Expectations converge as you continue to sample. Okay, that's the whole stack. What we need to know for our purposes is that you can write a Metropolis-Hastings algorithm, and we're going to figure out how to deploy that generally for arbitrary graphical models and arbitrary programs. Right? But knowing that this exists and being able to jump off into it is a very, very useful thing. In your homework, I think we do ask you to demonstrate that a Gibbs sampling transition operator is such that detail balance holds as well, so that you can actually show that a Gibbs kernel or a Gibbs sampler is a special case of Metropolis-Hastings algorithm, which means that all the same stuff applies, despite the fact that the algorithms look pretty wildly different, right? Cool. So that's that's actually in your homework. We talked about the invariant distribution statement being an eigenvector problem. That's pretty cool. It's worth thinking for a second about how independent Metropolis-Hastings satisfies, basically yields a valid sampler. And a very simple thing to really solidify your understanding of Metropolis-Hastings and Gibbs sampling is to is to actually use them to sample from a multivariate normal. In particular, a correlated multivariate normal. You will learn basically everything you need to know, and it's like 20 lines of code to do it. Basically, you just make a correlated Gaussian and then sample from each of the conditions in the Gibbs case, or choose a Q and go in the Metropolis Hastings case. And this report is in the readings. I really highly recommend that you, if you're interested in this space and you are like, Markov chain Monte Carlo is cool. It's a beautifully written. Radford Neal is just an absolutely stunning writer. It's marvelous. It's where I learned all this stuff from. So I recommend you check it out. Last little bit of trivia. If you're interested, you can leave now if you want, but I would ask what the Metropolis Hastings algorithm has to do with the hydrogen bomb. Anybody know?
Was it developed to model how the chain reactions in atomic bombs happen?
So like the specific science we can go into, but you should look at the author list on the Metropolis Hastings paper, and you will see that the senior author on the work is Edward Teller. Which is, he's the guy who invented the H-bomb. And as a very, very weird bit of trivia, and for the Russian speakers in the room, the only Russian that I actually know, I memorized from a very short in-person conversation with Edward Teller, which is completely, totally crazy. But actually met the man, shook the person's hand, and then 40 years later, 30 years later, or whatever, when learning about 20 years later, when reading about and learning about this, I was like, what? The guy who invented the hydrogen bomb is also responsible for, the most fundamental inference algorithm in modern Bayesian statistics? That's crazy. Anyway, another bit of trivia. He got the front of one of his feet cut off by a trolley when he was a kid. That's what we spent most of our time talking about. It's random, crazy, Anyway. More questions or anything?
Do you know what physics problem they use it for initially? Like I sort of knew that it was a bunch of physicists that did it, but I don't actually know what they calculated using it.
I think I actually don't know. I would have to go back and go in and figure it out. But clearly, like any physical system and its configuration, the only way that you can actually explore it in simulation is to write down the Boltzmann distribution or whatever for the physical system and then move it around, right? And I would imagine that they were probably looking at simulations of very small physical systems, like, for instance, what happens in a heavy atom when the number of neutrons is increased or something like that. That's what I would guess, and they'd probably want to simulate that. Because they were doing everything with pencil and paper, I have literally no idea what they could possibly have been doing. But clearly, a physical simulation of some system related to their efforts, or it could have just been hey, look, we can do this. Right? It's been a long time since I looked at the paper, but the original paper.
Sorry, I have a question for the slide we're right now on. So why is the Metropolis Hastings transition equal to like the proposed distribution times this A, which is just like the minimum of one and the
So the transition operator, this is awesome. This was a confusion for me. I totally get it. I was always confused by this. It's a really good question. The transition operator is, I'm in X and I'm going to go somewhere. And this distribution actually has an atomic mass at stay where you are. So detail balance, this is in the notes as well. It's very clearly satisfied when X and X prime are the same, because both sides are exactly the same, right? In other words, this is the same as this. But the transition operator is, I'm going to go to x prime, right, with some probability. Right, so the going to some prime, the probability of getting to x prime is the proposal probability. Like you have to actually propose, like it's a two-step process. The first thing you do, and like the first thing is you propose x prime from x given q. So that's the first part. And then you go to x prime with some probability, right? And you stay at x with 1 minus that probability, right? So you get the alternative, like you can also do this in a much more gory, nasty way and write down x to x prime, like the transition operator as x to x prime times x prime plus Dirac on x with probability 1 minus, and that would be the full transition operator, right? That's the full conditional distribution. There's a point mass on staying in the same place, and there's a mass associated to going to the value of x prime, right? And those two masses are controlled by A. So there's, and that is actually a probability, and that's why you need the min 1, so that it is actually a probability, right? Does that make sense?
Yeah.
I can tell.
Okay.
I can tell the actual answer is no, and you're saying yes to be polite.
Kind of. I might need to reread some stuff afterwards.
I think just actually doing this out by hand, like just literally doing this thing by hand, it will make sense. Yeah. Good question, though. More?
Yeah. So I'm a bit confused here between intuitively what does it mean for an expectation to converge, which is when we'll terminate our Metropolis Hastings loop, and equilibrium or detail balance.
Okay. So detail balance gives you a stationary distribution, right? Ensuring that this condition holds gives you ergodicity, right? Ergodicity gives you these limiting behaviors for the Markov chain. Okay. So we design a transition operator using detail balance so that we know what its stationary distribution is, and we ensure that we pick a Q such that this holds so that we know that the thing is ergodic. And then we can apply the strong law of large numbers and compute expectations that converge. The only thing that I think is somewhat missing in the question, the very nice question that you asked, is that in fact, like from a semantics point of view or a programming languages point of view, like we should never think of this as the sampling process as ever terminating, right? It's just there is an infinite sequence of samples, right? And your expectation will the expected expectation that you're computing will only get better as more and more samples are generated and consumed. Does that make sense?
I think so. Yeah. But I think I got confused in the part that, so when you say detail balance or equilibrium, it means that the distribution of going forward and backward is equal. Am I wrong there? And then in my mind, I was thinking, how is that different from convergence?
We're in general going to how to explain this. it's a sticky ball of yarn to actually unpack when you start thinking about it. I'll give you that. So I'll try to say it again. So the word that bothers me about what you were saying is equal. There's no like this distribution, this vector is indeed equal to this vector if detail balance holds. That's what this statement says, right? Okay, so true. But the problem is that we don't have access to this vector. If we had access to that vector or this distribution, we wouldn't have to do any of this sampling business. We wouldn't have to do anything. We would just, compute expectations with respect to P star, right? And in fact, generally speaking, we're going to be actually looking at population averages, and we're going to start with the other thing that we kind of hand wave over here is that you should really where it gets really confusing is when we start talking about sampling in this and this. Where did it go? Sorry. Give me a second. Maybe it's here. Where it gets interesting to think about is that we have several ways of simulating from the Markov chain, right? But really, what we're really talking about, particularly in continuous spaces, we're talking about a vector, and we're talking about discrete spaces here. But we have a vector with an element of 1 in it, right? And there's a couple of ways to simulate a Markov chain. One is to do this linear mapping thing where you're multiplying by the transition operator. But the other way that we're really talking about is these algorithms take that 1 that's in the vector and move it into another bin, right? And then they move it into another bin, and they move it into another bin, and they move it into another bin, and so on and so forth, right? So as time goes on, this element is going to be in the bins of different bins of vectors, and the amount of time that it spends in each bin is proportional to the equilibrium distribution of the Markov chain, right? But in order to get to that equilibrium distribution, you have to bounce that particle around in those bins according to the algorithm for a very, very long time. Does that make sense? Okay. Yeah. Thank you.
Okay, I'll have to think about it a bit more, but yeah, thanks.
Yep. More? Questions, comments, worries? All right. If not, thank you for your time and attention. Hasta luego.